Okay, so I'm just going to do a bunch of practice problems and try to explain all of them because practice is the best way to learn these forces. So once again, we have our three forces: dispersion, dipole, and hydrogen bonding. So we'll just go down the list. So C6H6. This C in general, CC and CH bonds are nonpolar. So if it's nonpolar, it's going to be dispersion. Um, and then HBr. HBr is Br is very electronegative, so it's going to pull this H atom. So because of that, it's going to become polar. But so polar would mean dipole. But you can check to see if it's hydrogen bonding, and hydrogen bonding, if you remember, is only significant in these three atoms, FO, fluorine, oxygen, and nitrogen, and it doesn't match. So it's going to be only polar. So it's going to be dipole. But if you remember, dispersion forces occur in all molecules, so all these will have dispersion forces. So once again, right off the bat, you can put dispersion forces, and then H2CF2. Okay, so H2CF2, we see that it has an F, but the F's not bonded to a H, so it's not hydrogen bonding. But the F is going to create, since F is so electronegative, it's going to be a dipole, just because the F's going to make this molecule polar, and because it's polar, it's going to become dipole. And also, if you look at the Lewis structure, it also makes sense, or the Vesper model, because H2CF2, right? C is going to be in the middle, and then you're going to have you can have like let's say one H over here, one H in the back, and then F, and then F. And this is a tetrahedral structure, but even though it's tetrahedral with no lone pairs, it's not nonpolar because of the fact that these are different elements. Like it's going to be pulling harder, like where the F's are, but the hydrogens aren't as powerful as the F's, so it's going to make this structure polar. So in general, what I see it as is that if it's different elements, like if it's not all the same element, it's usually going to be polar. So next, H2. H2 is just a diatomic molecule. It's just one hydrogen bonded to another. So that's going to be it's going to be a shape like this. It's going to be like that. And since it's almost like perfectly spherical, it's going to be dispersion, and dispersion forces happen in everything, and it's going to be nonpolar, so it won't be dipole. H2O2, you see that the O is attached to the H. That's going to instantly tell you that it's a hydrogen bond, because hydrogen bonding is with these three, and it matches. It's with oxygen. So it's going to be hydrogen bonding. It's going to be hydrogen bonding is a type of dipole, so you can put that too. But technically, hydrogen bonding is a type of dipole, and then finally and dispersion forces, dipole, and hydrogen. Next, we have CH3CN. You have to be careful here. You see that the H is connected with the C. When it's written like this, like CH3, the H3 is bonded to the one on the left, so it's going to be bonded to the C's. So the H's aren't going to be connected to the N, meaning that it won't be a hydrogen bond, but the N is still electronegative with and since it's strong, it's going to pull the electrons more, making it obviously it's always dispersion forces, but the N's going to be electronegative, making it dipole. And since it's more electronegative, it's going to be pulling those electrons more, and if you pull the electrons more, it's going to become polar, making it dipole. Next is this long molecule. CH3, CH2, 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 CH3. Once again, CC and CH bonds are considered nonpolar because they act that way. So since they're nonpolar, it would just be dispersion forces. H2CO. So the H2 is bonded to the C because it's next to the C. So the H is not connected with the O, meaning it won't be hydrogen bonding. But obviously, with all molecules, there'll be dispersion forces, but this O is, since it's electronegative, it's going to be pulling the carbon's atoms, making it a polar molecule. If it's polar, that means it's dipole. Now O2, once again, we have a diatomic molecule. It's going to be pretty spherical in shape, meaning it's going to be nonpolar. It's sharing its atoms pretty evenly, so it's going to be just dispersion. CH2Cl2. So the Cl right here is electronegative, so it's going to be pulling these atoms more to it. So that's going to make it polar, and if it's polar, it's going to be dispersion and dipole. Dispersion forces happen in everything. Dipole is because it's polar. And then we have CH3, CH2, CH2, OH. So this OH tells us that like all these bonds, CH, 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 all of these are nonpolar. But this one tells us it's a hydrogen bond because it's hydrogen connected with oxygen. So since it's hydrogen, it'll be a hydrogen bond. Technically, it's also a dipole. Hydrogen bonding is a type of dipole. Dipole bonding. And then finally, dispersion forces, as with all atoms and molecules. Now this one, rank these four compounds, let's say from weakest to strongest. So we'll go down the list. This is actually a different type of bonding, but it's easily coverable. So RB is a metal because RB is a metal. So that's going to be a metal, and it's a cation and an anion. So that's going to be an ionic bond. If it's an ionic bond, it's going to have a type of bond intermolecular force called ion-ion interaction. So ion-ion interactions are actually stronger than hydrogen bonds. So we can quickly cover ion-ion interactions. So once again, the point of this is if you have a molecule, let's do a hydrogen bond, HF. The actual intermolecular force is not the one in the middle. It's the force. It's the force between the molecules, meaning this right here is a polar covalent bond. Right here, it's a polar covalent bond, and those are incredibly strong. But what we want is the intermolecular force between this. It's the force between these two. And this force is the intermolecular force. That is the hydrogen bond. And so when you have something like RBF, or an easy one is NaCl, salt, when you have NaCl, this right here is an ionic bond right between there, because it's a cation and an anion. That is a ionic bond. But the force between them, it's going to attract between them. This force right here is called an ion-ion, because this Cl minus is also attracted to this plus. So, and these forces are actually stronger than hydrogen bonds. So that pretty much covers ion-ion. But going back to this problem, so we have an ion-ion, which is actually stronger than hydrogen bonding, because of it's a full charge. Like RBF, it's a full charge, whereas the other one is only a partial charge. So CO2, if you draw out its Lewis structure, which actually I can draw it out really fast. CO2. So, and you have your lone pairs over here. But this would be a linear structure, making it nonpolar, because there's no lone pairs, only two domains. So it'd be a linear structure. So, and linear means that it's nonpolar. So CO2 would actually just have dispersion forces because it's nonpolar. CH3OH, the OH gives away that it's a hydrogen bond. So it'd be a hydrogen bond, and all, like dipole, but it's a dipole and dispersion, but we can just put that's a hydrogen bond. And finally, CH3Br. We look for any hydrogen bonds. There's no hydrogen bonds because there's no fluorine, oxygen, or nitrogen. So the final thing is the fact that Br is more electronegative than C or H3, so it's going to pull the electrons more, making it polar, making it a dipole. So now we just rank it. So let's say I said weakest to strongest. So the weakest would be CO2, remember, because it's a dispersion force, and dispersion forces are the weakest. Next would be dipole, which is CH3Br, because it's a polar molecule. And then hydrogen bonding is stronger than dipole, so you'd have CH3OH. And finally, ion is the strongest because of its full charges rather than partial. So then you would have RBF. So that's that problem. Next, for these problems, it's which one is stronger. So O2 or Cl2. So for this, what you have to know is not only these three bonds, but what happens if you have two of the same. For example, in this problem, O2 and Cl2, both of these are actually, both of these molecules, or compounds actually, both of these compounds are diatomic. They only have dispersion forces, and we know that dispersion forces are weak, but how do we tell which one's stronger? Now if you go back to just the basics, if you have a nucleus, right, and then you have your electrons around it, the more like the plus charges in here are pretty attracted to the negative charges, so it's going to be a strong force. But the more levels you have, the less strength this plus has on these negative charges, because it's getting farther away. So the bigger this molecule gets, these electrons are so far away that they have more freedom. Like they can move away farther because the plus charge isn't pulling on them as much. It's like if it was an overprotective parent. This parent can easily grab a child here, but if the child's all the way over here, this parent's going to have a hard time grabbing onto that child. So this child over here has more freedom. That's what, and that's what it means when something's polarizable, or more polarizable. Meaning, the bigger something is, when we're talking about, let's say, dispersion forces. Going back to the example of O2, if you have oxygen right here and oxygen right here, it's gonna be like one electron can be over here more, so it's gonna create a partial negative and a partial positive. But if it's a bigger molecule, if it's like Cl, right, Cl is gonna be larger, and if Cl is larger and the electrons in the far can move more, if these electrons can move more, then more electrons will be coming over here. So much more than this. If, let's say, only like one electron was over here, it would create a negative charge. But let's say like 5 electrons come over here, this would create a much bigger negative charge over here, and then a much stronger positive charge over here, just because it's bigger. The electrons can shift more because they have more freedom, so they can move over more. So going back to this problem, if you're faced with a compound with the same intermolecular forces, such as O2 or Cl2, you can look at your periodic table. Let me just show you. You can look at the periodic table and then see that Cl, you can look at molecular weight, which tells you how many the weight, the amount of atoms, and so the larger the weight, the more atoms are there, and the bigger the molecule is. The bigger, since this molecule will be bigger than O2, is there two of these, it's going to be around 70, where this is only going to be 32. A bigger molecule is going to be able to shift. It's going to be able to shift more than something that's smaller. So that means that Cl2 will be the stronger force. So going on with that example, SO2 or CO2. Once again, you can look at the periodic table. So since the O2s are the same, we can keep those independent and just look at S and C. And S has a it's heavier than C, so that means S is going to be a bigger molecule because it has more weight than CO2. So that means the bigger the molecule, the more likely it's going to shift around. The more likely it's going to shift around, the bigger the charges. The bigger the charges, the stronger it is. And so therefore this one is SO2. And then finally HF or HI. Well, HI is just a polar molecule, but HF is actually a hydrogen bond. And if you remember, the HI would just be dipole, but this would be a hydrogen bond. So hydrogen bonds are stronger than dipole, so HF would be the answer. And finally, C4H10. These are called isomers, where the formula is the same, but they're structurally different. So this one is more it's more kind of loose or disorganized, whereas this one's very tightly compact, and the H's are just attached to all the C's. So just looking at this, what happens is that when something's very structured, it has less surface tension. So if you have this molecule hitting other molecules just like this, there's more points of contact for each point, a part of this compound. More places for the dispersion forces to hit. Dispersion forces happen between all atoms, and individually they're weak, but collectively they can become strong, because if there's a small dispersion force every single place here, that's going to be a really strong charge, whereas this one, there's not as many, because it's going to be very compact. It's going to be much less than this one. So this one will actually have the strongest. It will be stronger than this one. So to recap, if you we have our various van der Waal forces, which are hydrogen bonding, dipole, and dispersion forces, and ion. But so if you have two forces or two compounds that are the same, like what I showed you, O2 or Cl2, if you have two that have the same, whenever you have two compounds that are the same, the first thing you want to do is look at molecular weight. So whenever you're doing a problem like this, first look at what are the forces. What are the forces that they have? See which one's stronger. So we looked at these two, and we saw that they both have dispersion. They're both nonpolar, so both of them have dispersion forces. The next thing we look at is we look at molecular weight. Molecular weight tells us which one's bigger. The bigger something is, the more polarizable it is. The more polarizable, all that means is that the electrons can shift more. If the electrons can shift more, then it's going to have a stronger charge. Because once again, like just oxygen. If only one electron comes over here, right? It's gonna be a kind of small charge. But for Cl, if this is a big molecule, right? And then let's say 5 electrons come over here, that's gonna create a much stronger charge than something that O2 would. The forces between the molecules will be a lot stronger in ClCl. So look for molecular weight because that'll tell you how big the molecule is. So, and then finally, look at the structure, because the structure tells you the surface area. The bigger a structure, like for example on the previous one, if let's say you just had CH3, if it was between CH3 and CH